What is Higgs boson and Higgs field? We are made of star stuff. Everything you know, even yourself, is all made of the same fundamental particles. But at the start of the universe, none of these particles had mass. They all moved at the speed of the light. It is only because the particles got their mass from a fundamental field linked to the Higgs boson could stars, planets, and life form. What is the Higgs boson? Back in 1964, English physicist Peter Higgs submitted a paper to a scientific journal that contended that all of the space is filled with a kind of the field which came to be called as Higgs field that imparts mass to the objects. Scientifically, mass is defined as resistance which is offered by a body of matter to a change in speed or position on the application of a certain force. Push a ping pong ball through the air and it moves almost without any resistance, but push that same ping pong ball through the water and it will be much harder to push then. The Higgs field is a bit like water. In 1970s, physicists realized that there are very close ties between the weak force and the electromagnetic force. They developed the basic equations of a unified theory which proposed that electricity, magnetism, light, and some types of radioactivity are all manifestations of a single force known as the electroweak force. This force is carried by the photon and the W and Z bosons. But there was a problem. The equations predict that these particles have no mass, and physicists already knew that the W and Z bosons have certain mass. Peter Higgs made a proposal to solve this problem. He proposed that W and Z boson interact with a force which is called the Higgs field. The field gives masses to these particles in exchanged in weak interactions, but not to the photons exchanged in electromagnetic interactions. The stronger a particle that interacts with the Higgs field, the heavier the particle ends up being. Now, what is the standard model in the physics? The standard model first began taking shape in 1897 AD when English physicist J.J. Thomson discovered the electron, and it wasn't considered complete until 2012 with the discovery of Higgs boson recently. Our universe is comprised of 6 quarks and 6 leptons. These are the particles that make up atoms. Quarks within the protons and neutrons and electrons surrounding the nuclei. 4 fundamental forces are at work in our universe. They are electromagnetism, the strong force, the weak force, and the gravity. Unfortunately, the standard model cannot account for gravity, so for now we have to just ignore it now. The remaining 3 forces result from the exchange of force carrier particles or Gauss bosons. Particles transfer discrete amounts of energy by exchanging bosons with each other. Each fundamental force has its own corresponding boson. The electromagnetic force is transmitted between the electrically charged particles by the photon, which is actually massless. The weak force is transmitted between quarks and leptons by the W plus, W minus, and Z Gauss bosons, which are massive particles, with the Z boson being more massive than W plus minus. The strong force is transmitted between quarks by 8 glucons, which are massless. Quarks and glucons are color charged. Color charged particles exchange glucons in strong interactions. 2 quarks can exchange glucons and create a very strong color field that binds the quarks together. Quarks constantly change their color charges as they exchange glucons with other quarks. Because glucons themselves have a color charge, they can interact with each other. The physicist Leon Lederman once famously dubbed it the God particle. Lederman coined the phrase for the title of 1993 book, which entitled The God Particle. If the universe is the answer, then what is the question? What does the Large Hadron Collider have to do with the Higgs boson? The Large Hadron Collider LHC, which opened up in September 2008, is located at the European Council for Nuclear Research. It is a 17-mile long, that is 27.35 kilometer ring that runs primarily beneath Geneva, Switzerland, and it uses around 9,000 superconducting magnets to corral millions of protons that are circling the ring in both directions at close to the speed of the light. At specific points along the ring, the 2 proton beams collide with each other and produce sprays of the particles, which are observed by enormous detectors. On July 4, 2012, physicists around the world gathered in meeting rooms to hear and see a press conference being given at CERN. The purpose of the press conference was to announce the discovery of the Higgs boson. In the audience was 83-year-old Peter Higgs. Also, he was present there. In 2013, a year after the discovery of the Higgs boson, Peter Higgs, along with Francois Englert, was at last honored with Nobel Prize in Physics. On the day of the Nobel announcement, Higgs, who doesn't actually own any cell phone or have an email, went to the store, and it was only when he bumped into one of his neighbors that he found out that he'd actually won the prize. Now, what is the Higgs field? The Higgs field differs from other fields such as electromagnetic or gravitational fields in that it is unchanging. The strength of electromagnetic field waxes and wanes depending upon the distance. The strength of a gravitational field is also determined by the distance. Stand next to a black hole and you will experience a much stronger gravitational field than you would be standing on the Earth. By contrast, the Higgs field appears to be the same no matter where you are in the universe, and it appears to be a fundamental component of the fabric of space-time. The property of mass is a manifestation of potential energy which is transferred to the elementary particles when they interact with the Higgs field, which contains that mass in the form of energy. Spin is the intrinsic angular momentum of an elementary particle. In quantum field theory, the spin of a particle is related to its behavior. For example, bosons have an integral spin 0, 1, 2, etc. and so can occupy the same quantum state at the same time. In contrast, particles with half integral spin, that is 1 by 2, 3 by 2, etc. cannot. In the standard model, the components of matter, electron, quarks, etc. are half integral spin particles, while the particles which transmit force, such as photon, W and Z, glucon, are integral spin particles. The Higgs field is the only scalar or spin zero field. The Higgs field imparts large masses to the W and Z Gauss bosons. Their masses affect how far the W and Z bosons can travel, thus confirming the weak force extremely short range. The Higgs boson is a massive scalar boson having zero spin, no electrical charge and no color charge. As predicted, it has a hefty mass of 125 gigaelectronic volts and a predicted mean lifetime of 1.56 into 10 to the power minus 22 seconds. The Higgs boson has been observed decaying into a pair of bottom antibottom quarks, the two W bosons at tau anti-tau pair, two Z bosons and two photons. It is also predicted to decay into two glucons, a muon anti-muon pair, and possibly other particles too. While the Higgs field generates the masses of the leptons, the electron, muon and tau, and the masses of the quarks, it does not generate mass for the photon and the glucon. And because the Higgs boson is itself massive, that means that it must itself interact with the Higgs field. The future of the Higgs field physicists now believe that 95% of our universe is not made up of ordinary matter, but consists of dark energy and dark matter. Dark matter has mass, and physicists have suggested that dark matter particles could interact with the Higgs boson decaying into dark matter particles. Even though finding the Higgs boson appeared to complete the standard model, in effect scientists have not stopped looking into this elusive particle. Since 2012, one of the most important things learned is that Higgs particle breaks down, and more will be learned about the elusive particle during 3 of the LHC, and especially when the high luminosity upgrade to the particle accelerator is finished in 2029. This will allow the LHC to have more collisions, giving scientists more chances to explore strange physics like things that don't fit into the standard model. After the upgrade, CERN thinks that accelerator will make 15 million of these particles every year. This is a big difference from 2017 when LHC just made 3 million Higgs bosons at that time. This could be the key to finding other types of Higgs bosons. Theories that go beyond the standard model of particle physics also predict that there could be up to 5 different types of Higgs boson, which may each be less common than the main Higgs boson. Even before the upgrade, scientists had clearly given us hints of a magnetic Higgs boson, and the mystery has yet to be resolved further. Thanks for watching this video.